I really like this material. Like I said, it is enrichment material. It's not something that is strictly required for any of the Pintos assignments, but the more you understand of this kind of stuff, the easier it makes understanding the features you have to implement in Pintos, how to build them, and how they all hang together and work. So even though it may not be strictly required, I think it'll be of benefit to you down the line. Plus, this just happens to be one of the coolest things in my mind that operating systems do. And it's this relatively unexciting seeming functionality of signal handling and how it's actually built in the operating system. I believe that CS24 still gives you the opportunity to look at signal handling as a mechanism. If I remember correctly, Adam has that as part of an assignment. I'll have to ask and make sure this is still true. But signals in Unix are basically like hardware interrupts, but in user space and user mode. You can register signal handlers for illegal instructions. That's directly mapped to a hardware interrupt. Divide by zero. That's directly mapped to a hardware interrupt. Timer ticks, also a hardware interrupt. So you can actually consider signal handling to be a way of exposing some of these hardware capabilities, interrupt capabilities, into user programs. Besides that, there's also a bunch of other ways in which signals are used that are purely software related, like the ubiquitous kill command when I need to stop a process from running, or I need to signal to a process to reload its configuration, or other things like that. There's a lot of other ways signals are used. So the way that signals are typically used is that a program who wishes to receive signals will register a handler for those signals, and then the OS kernel is responsible for calling the handler when the signal actually occurs. So you have a signal delivery mechanism implemented inside the kernel. So this will be a typical way that it's done. You have this function call signature. I don't know if you've seen this syntax before. It's actually in Pintos as well, because there are operations on lists and other collections that allow you to call a function on each thing. So SIGT is the name of the type, and it is a pointer to a function that takes an int argument and returns nothing. So that's the way that this is defined. And in this case, the int is the numeric, how do I say it? It's like each signal has a number associated with it, and the argument to the signal handler is the number of the signal that occurred. So, like, I don't know if any of you have ever typed kill -9, but 9 is the number for sigkill, which is the signal that cannot be ignored. It's the signal that will always terminate a process regardless of whether it tries to handle it or not, whether it's wedged or not. So you would never see a 9 come through, but you would see other signal numbers come through corresponding to the type of signal that actually occurred. And so there's this function here, signal, where you say, this is the kind of signal I want to handle, and this is the function I want you to call when the signal occurs. And so that is a system call, and it tells the kernel to register that handler for when that signal is sent to that particular process. Okay, and yeah, you can look in signal.h. This is a standard header for this kind of functionality. This is a classic example I would use when I was teaching CS24 and showing how signals can be used. It has two signals that it's handling. You'll notice that we have two calls to signal, one for sigint. Sigint is what Unix systems send to a process when you hit Control-C to try to interrupt it. That's what int stands for in this case. And then sigalarm, which also should be pretty self-evident. This is for when a timer elapses and a sig alarm is sent to the process that requested it. So alarm 1 says, please send me a sig alarm in 1 second, more or less. It's approximate. And so when this alarm goes off, it'll call handle sig alarm, which you can see up here, just prints hello, and then immediately ask for another alarm in 1 second. So you can imagine that this program will print hello, 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 once a second. And of course, we want to be mischievous, so we also handle the sigint, which is control C, and we taunt the user. We say, haha, can't kill me, control C, control C. It turns out there's a bunch of other ways to kill a process, so it's not like that's actually going to be that challenging. I think control backslash does it, and yeah, I should probably stop there. I'm pretty sure control backslash sends sig quit, which we're definitely not handling in this program. So that's that. It's a pretty straightforward program, and hopefully illustrates how signals work at a perhaps a not particularly useful level, but certainly illustrates the concepts. We also have this other function, which to me is the exciting one, called sigaction. This is another system call that can tell the kernel that a process wants to handle signals, and you'll notice it's significantly more complex. We still have the signal number that we want to handle, but we also pass in the sigaction thing and this other sigaction thing that we use to configure the signal handling mechanism. And this lets us have all kinds of control. It allows us to control which signals are delivered before other signals. It allows us to control what information is passed to our signal handler. It gives us a huge amount of control over the signal handling mechanism. And the one that's more interesting is sigact. So this is a handler function that a user process can provide. And notice it gets the signal number, it gets the siginfo thing, which tells the handler some useful information about what happened. And then we also get this other thing, void star. So if you see a void star being passed around, it's always about to get exciting. This is the machine context. So this is the register state of the process when the signal occurred. And so this allows you to do some really crazy things through signal handling in your program. So siginfo, as I say here, the sending process ID, if it wasn't you, because remember, processes can send other processes signals, the memory address that caused the fault, so you can register a handler for sigsegv, which is what happens when you dereference null, but it happens in a lot of other circumstances as well. And the siginfo will tell you what instruction caused the fault. And it'll tell you what address was being accessed when the fault occurred. So you can use this to build some very sophisticated mechanisms, and it's leveraged in some pretty amazing ways in very sophisticated software. Then, as I was saying, the context is this machine context thing, which is obviously platform or architecture independent. If you're running on a 32-bit operating system or a 64-bit operating system on the same processor, it'll expose different registers because you use different registers in these different operating modes. And it allows you to tweak things, including the instruction pointer of the process at the point that the program was interrupted. So this allows you to build user space threading libraries. And this used to be a CS24 assignment. We built a cooperative user space threading library, so cooperative multitasking. And then we updated it to build a preemptive multitasking version of the same library. And it's very straightforward to do through this signal mechanism. So very, very powerful mechanism. The operating system grants a tremendous amount of control of a process over itself, but obviously it does that in a way that doesn't affect other processes. So it's just an absolutely remarkable thing. The way that this signal delivery mechanism works is useful to understand. Again, maybe you have never used signals in your own programming, and that's fine. One of the reasons why I think it's helpful to understand this is because it sheds light on how hardware interrupts are implemented in the processor, because the signal handling mechanism is very similar to the way that interrupts are handled on the processor. So the kernel has these 2-bit vectors. Each vector has 1 bit for every kind of signal. So sigalarm will have a bit, sigint will have a bit, sigquit will have a bit. All of these things have a bit associated with them. And the pending bit vector is zeros, but when a signal is sent to a process, the pending bit for that signal is set to 1. so that the kernel now knows there's a pending signal of that type to deliver. Now, that has an implication, which is that if I have more than one signal occur and I haven't handled the first one and the pending bit is still set for it, the new instance of that same signal comes in. Well, the pending bit is already 1. And so what you notice is that signals are great for knowing that at least one instance of a thing has occurred. But it doesn't tell you precisely that this many of this kind of event occurred. Like if I'm mashing Control C and I hit it 5 times before the first one has been handled or delivered, well, it's just going to have that SIGINT flag set once. The block bit vector allows the kernel to control when signals should be delivered and when they shouldn't be delivered. And one of the things that is useful about this is that when a signal is being delivered, the block bit is set to 1 for that signal, so that a handler for a given signal won't be interrupted by the same signal again before that handler has completed. So the blocked bit vector makes sure that each kind of signal is delivered sequentially. Like you don't have 2 instances of the same signal type interrupting or being handled in a concurrent manner, because that would just lead to chaos. Okay, so yeah, this is all virtually identical to the way that hardware interrupt handling works, which is why I think it's a useful thing to be aware of. And if you do any Unix system programming at any significant level, you're going to run into this kind of behavior anyway. Okay, so the question of the day is really, how does the kernel provide this signal handling mechanism to user processes? Because it's remarkably sophisticated as you think about all the nuances and all the details of how this thing operates. So you have a question: when is a signal delivered to the receiving process? What if the process is running on the CPU? What if it's not on the CPU right now? So you can, let's say that you have parent and child processes. The child terminates, the parent gets a sig child, but the parent's not currently running. So how does that mechanism work? How does signal handling affect process scheduling? If a process has multiple signals pending, how does the kernel take care of delivering all of those pending signals to the process? And one of the things that I want to mention up front is we're going to be talking about this in a decidedly single-threaded context, meaning that we're talking about processes without multi-threading, particularly kernel-supported multi-threading. And part of the reason why is because when you have multiple threads, now a given thread can say, I don't want to receive signals. Or you can have thread A register a signal handler, and then when the signal's delivered, it's received by thread B in the same process. And so it's hard to do signals in multi-threading as it is. And typically when you're writing programs like that, you have to take careful steps to make sure that signal handling makes sense in the program. So we're just going to talk about single-threaded processes today. Almost always, in fact, I should say very frequently, a process is not running when a signal is sent to it. You might call kill because you have a process that's wedged and it's not responding because it's stuck in some weird state and it's not making any progress and you don't know why. Maybe you've seen this on Mac OS when you go to right click on an application and it says application not responding, and you think, oh, great, now I've got to do something about this, or it says force quit, those kinds of things. Another one, like I mentioned, sig child can be sent to a parent from a child that terminated, and the parent is clearly not running when the child is terminating. Maybe you're waiting, maybe you're blocked on console input, or you're blocked on disk input, and the user decides to suspend the process using Control Z or something like that. Lots of things can happen. So we distinguish between generating the signal, which means queuing up some information to say, hey, this is a signal that's going to be delivered in the future at some point, and then the act of actually delivering the signal to the process is supposed to receive it. So we separate those two things because that makes the problem much easier to understand. So you have signal generation. The kernel updates the data structures of the receiving process to record that the signal was sent. And then signal delivery, which is that the kernel forces the process to respond to the signal. Okay, and we'll talk about that mechanism today. There may be a significant amount of time that passes between the two, depending on the circumstances of signal generation and the state of the process and so forth. Okay, the way that these signals are tracked inside the kernel is through a handful of data structures that are associated with each process. Just like you guys have seen kernel threads, and they have various data, data members that correspond to facilities that the kernel provides for threads or processes or whatever. There's some things devoted to signals as well. So we have the pending and blocked bit vectors, which are per process. Okay, and that allows you to record that a signal is about to be delivered or that a signal is blocked from delivery. There's also a few other details which I have represented on this slide in sort of a schematic type view, because obviously this will vary from operating system to operating system. We have a signals linked list, which is actually a list of the signals pending delivery. So we actually have some linked lists that we just queue up signals on for delivery. And this is for a couple of reasons. And then we also need to know how the process has requested that signals be delivered or how they be handled. And so that's a SIG-hand array. And this array contains an entry per signal type. And it'll have things like, what's the handler to call? Is it the simple handler or the sophisticated handler? Is there other configuration that I need to know about? Also, it'll have things like, should I use default signal handling responses for this kind of signal? All of you have been writing C and C++ programs, I'm sure, for quite some time. And you don't think about this. It's because the kernel sets up some default responses to signals. Like when you get a SIG-seg-v, the default response is to kill the program. Usual, right? SIG-int, when you hit Control-C, the default response is to terminate the program. Same with SIG-quit and so forth. So that SIG-hand array will record that kind of information, and then the process can modify it as it sees fit. Okay, talked about all of this kind of stuff. All right, yes, there's nothing new to add to this slide. So when you send the signal to a process, the kernel has, because the software developers try to follow good encapsulation and everything. And so there's a function that's called to update the data structures for the receiving process. And so in Linux 2.6, it was this function specific send sig info. This stuff has since Linux 2.6 kernel been refactored and updated, but this is definitely representative. You definitely aren't missing out. And so the function goes through and says, do I already have a signal of that type? Because remember that if I've gotten a signal of a given type, the pending bit will be set to 1. And if I get subsequent signals of the same type, I can't really record them. And so if there's already a pending signal of that type, there's no reason to add another SIG-info struct to the list. Okay. The one exception is these real-time signals. Real-time signals are special in that every instance of a real-time signal is delivered. So those would be queued up on the list. And that's the big reason why we queue these things up. If the process is ignoring the signal, or it's set to a default handling mechanism and the default response is to ignore, then it doesn't do anything. This function becomes a no-op. So you can imagine that this thing is going to be clever and simply no-op if the signal is going to be ignored anyway. Okay. Otherwise, we add it to the signal queue and set the corresponding pending bit, and that's basically it. Now, another aspect of this is if a process receives a signal, now it can actually start running, right? Because it has some external stimulus that should warrant perhaps a response on the CPU. And so if that process was blocked on something or it was suspended because it was, either you have an older OS with a medium-term scheduler or the user simply suspended it, then it then gets moved to the ready state because it can run. It needs to respond to the signal handler. And as I mentioned here on the slide, there are some signal types that are not added to the signal queue. And part of the reason why is because they tend to affect the process's execution state. Sig kill, that's the numeric value for sig kill is 9, and that's the one that cannot be ignored. It's our safety release in case a process is completely run away and otherwise can't be terminated. Sig kill will always terminate a process. And then you have sig stop as well, which stops a process from being scheduled, so that removes it from the short-term scheduler. So these things are enforced immediately and from within the kernel. So we just need to record that it is pending, and then that's all we really need to do. Okay, I think that's all I need to say about this. There's other details, but I'll spare you them. Okay, delivery is where all the exciting stuff happens. Signal generation, signal recording is bookkeeping. And I'm sure that you have to think about concurrency as always because it's an operating system, but delivery is where all the exciting stuff happens. A process has to be running. It has to occupy a CPU for the signal to be delivered. Now, you might notice this, especially now that you've had some experience with Pintos. It's not just the process that has to be running. Obviously, it's not necessarily that you're inside the process yet. It's that you're in the kernel thread that corresponds to the process. So when you switch to a new process and you're getting ready to, so the scheduler is run, you've done your thread switch to go to the new kernel thread, and now you're running in the new kernel thread, you're about to go back into user mode to resume executing the process. And the kernel, before that switchover, can look to see if there's any signals about to be delivered. And that's when they would be handled. So this is sort of the background of the statement. Signals are only delivered to the currently running process. You have a flow something like this. Okay, so the scheduler runs just like I was saying. And now we have a new process. We switch to the process's corresponding kernel thread. We can access all the kernel data structures for that process. We can look at the signal state and say, are there any pending signals to deliver to this process? And if there are, then we do something. This is magic still. So we handle the signals somehow. And then once we're done, we go into the user process. We switch to the page table for the process so that virtual memory looks like what the process expects it should look like. And we restore the registers, we IRET, and go back to the process so that it can resume running. Now, there's two ways a signal can be handled, and these are what I already kind of alluded to in the previous slide. So either we have some default behavior. One of the default options is ignore. Another thing you can do is just say, I want to ignore this. So you can explicitly say, ignore this, even if it's not the default behavior. So you can do those things. Or you can have a user mode handler. Now, the signal handler exists in user space. And certainly we don't want to run the user space signal handler in kernel mode. That seems like a terrible idea. So what we do instead is we switch over back to user mode, run the signal handler, and then magic, right? So we still haven't completely explored how this is implemented yet. Now here's a more accurate picture. Again, this is reflective of the Linux 2.6 kernel. There may be various tweaks to the details of this mechanism, but it is completely representative for how this works. So we have these two ways a signal can be handled, and you'll notice if we have a kernel handled signal, the kernel can try to get through as many of these signals that are queued up as possible, because they tend to be handled in simple, straightforward ways for the kernel to do quickly and in kernel mode, okay? So if you have user process handled signals, it's a little bit more involved. You'll notice that we do this thing. Is it a kernel handled signal? No. Okay, we've got to go back into user mode, run the signal handler, and then we come back into kernel mode for some reason, return to user process, and then we go back to this normal operation of the process. So we have this like sort of hopscotching we're doing back and forth between the kernel and the user process. Okay, so that's why only one is delivered at a time. There is another function that encapsulates this signal delivery implementation. As you would expect, you want to see good encapsulation so that things are easy to reason about. And so that would be do signal. So you'll see me referring to do signal as we go through this discussion. Okay, delivery challenges. Well, first of all, when we go into the signal handler, you can think of it as running a completely different part of the program than we interrupted when we ended up in the kernel in the first place. So if we're going to get to the signal handler, we need to somehow set up a machine context specifically for running that signal handler, so that when we go back from the kernel into the user process, we run the signal handler, and then we need to hop back into the kernel to restore the previous context that the process was running in, to go back to the normal code. So that's kind of a little bit involved. Signals can interrupt system calls. I may be running inside of a long-running system call. Let's say I'm doing a read on a character device that happens to be the console because I'm waiting for the user to type something. And a SIG alarm goes off. Well, now my read call was interrupted, and so I need to leave the kernel and go handle the signal in the user process and come back. What do I do with that read call that was in flight? That's a question that you have to solve for signal delivery. Handlers can make system calls. So this is where it starts to get really crazy, right? I could be in a read call waiting for the console. A SIG alarm goes off, and in my SIG alarm handler, I write something to the console because I call printf. How does that work? So there's complexity here. I mean, this is why I love this. It's such a remarkably elegant and sophisticated mechanism. And then there's the third one, which is kind of crazy, which is the use of functions like long jump and sig long jump in the signal handler to go back to another part of the program. This used to be an extremely common mechanism for telling a server to reload its configuration. And hopefully it's not so common anymore, because there's quite a bit of risk and danger in doing so. But we'll spend some time talking about long jump and sig long jump toward the end of the discussion. Okay, so you can see that there's some complexity here. So what do signal does? You can see, you've got arrows here, right? And one of the arrows goes back to the beginning. So that should be your first clue that there's a loop involved. But we have a loop, and basically we try to find a pending signal to service. And the kernel will be clever. If there's multiple signals to service, it may be easy to deal with some of them, so it just gets them out of the way. And you also have this unusual thing that sometimes two signals may cancel each other, like a sig stop, which removes a process from being scheduled, I should say, and sig cont, which stands for continue, which tells it to resume being scheduled. So clearly, if you have a stop being scheduled signal and a resume being scheduled signal, those things annihilate. They disappear. So there's a few things like that. The kernel will go through and take care of as many of those things as possible. If you end up with no signals, either there were no signals or all of the pending signals were handled, then you can just go straight back to the user process. Using the mechanism you all should know and love by now, and certainly you will by the end of the third project where you complete user programs for Pintos. Now, if a pending signal was found, it's removed from the pending queue. And it's actually really important that the pending signal data is removed from the pending queue and the pending bit vector before any delivery to the user process happens. We don't wait for the user process to finish before removing it from the pending information, because that actually would turn out to be too constraining. So when a signal is going to be delivered, we remove it from the pending state immediately. Okay. If a signal is being ignored, do signal just ignores it? I mean, that's shocking, right? So there's a couple of ways you can do that. One is if you set the handler to sig igen. This is a special value you can use to tell the process to ignore a certain signal, which is like always tempting to people who first learn about this. You mean I can just ignore all my seg faults and my program will keep running? That sounds great. And then they do that and they don't realize that now chaos is descending upon the execution of the program. You'd rather have programs fail fast and visibly than to try to hide failures and instead quietly go insane. Nobody benefits in a world where things quietly go insane. So yeah, and so then there's a few others. Sig default for sig child is just to ignore. Let's see, do signal will check if the default action should be used. There's various default actions. Now I want you to look at this because it turns out that some of the default actions are pretty easy to implement. So terminate, kill the process. That's easy. I never have to really go back into the process context. Actually, I'm thinking about that. You would if there's add exit handler. So you may still make a quick flip into the user mode process just to take care of exit handlers and things like that if you have a termination scenario. Dump, which kills the process and creates a core dump. Ignore, stop, and continue. So we've already pretty much talked about ignore, stop, and continue, but these just affect the scheduling state. Terminate and dump, well, they end the process's existence anyway. So do signal takes care of that stuff. It's kernel level stuff anyway. Now, if we have a situation where a user process has provided its own signal handler, then we somehow need to set up for it to be called. Now, understanding the way the stacks are laid out is always your friend in understanding how this mechanism works. So we're in the user process stack. Remember, this is before the signal occurred. So we were in the kernel for some reason. Maybe we did a long running call. Maybe we trapped into the kernel. Maybe we got preempted. Regardless of how we ended up, we're going to have all this stuff. Remember, this first white section is what the hardware interrupt or software trap handler will push. Then we have the interrupt stub, which is this pink stuff. It probably looks pink to you. It looks pink to me. And the register state of the interrupted process. And now we're inside the kernel. So there's other stack frames of the kernel inside the kernel thread stack. Okay, so this is the state of our system when a signal handler has to be dispatched. Now, it's actually not hard to get the signal handler to run, because remember, the process has already said, here's the address of the handler I want you to invoke. So really all we have to do is go in here and change the instruction pointer to be the instruction pointer of the signal handler. And when all this stuff gets popped off, we end up back in the signal handler as opposed to in the regular, what we interrupted. The only problem with that is we still want to eventually get back to where the program was when it was interrupted. And so we can't just clobber this data. We have to make sure we save the old information somewhere. Now that's the first issue. The second issue is this kernel thread stack is going to be empty by the time we get back to the user process, because remember, we're popping stuff off of it as we leave the kernel. So this stuff is going away. Clearly, we can't store information about signal handler or what was interrupted on the kernel thread stack. So hopefully you're seeing the obvious conclusion, which is it ends up on the user process stack. So as I say here, you can't just overwrite the previous CPU state of the process. So we set up more information on the user thread stack, and that's how this magic works. So yeah, so I was already talking about this. So here's the first thing that happens. We're dispatching a signal. We're making sure that a signal gets delivered. So the first thing we do is we save the machine context of the program where it was, when it made the trap, when it was preempted, whatever. So we save that onto the user thread stack. And yeah, as it says, these details are used when the signal handler returns because we need this to go back to what was interrupted in the program. Then the kernel can modify the machine context to return to the signal handler, not the place that was interrupted. Everybody with me? I hope you're with me because it's a pretty clever mechanism. Okay, the next thing that has to happen is we have to set up because a signal handler is going to be invoked and it expects there to be a stack frame. It expects to see arguments. It may push local variables and so forth. So as I say here, if we're calling a one argument signal handler, we need to make sure the signal number goes onto the stack. This is the old CDECL convention. With the current AMD 64 ABI convention, you just put it into a register, and the old register value would have been saved in this context on the user stack. 3-argument handler, the details will go onto the stack as well. So you end up with something like this. And what's really cool about this, you remember when I was showing you SIG action, and SIG action had that weird magical argument at the end, which is the machine context of the process when the signal interrupted the process. Well, that's already on the user stack, register state of interrupted process. So the U context can just point to this data structure on the stack, and now the signal handler can see all the registers of the process when it was interrupted. It can see the instruction pointer, the stack pointer. It can see everything, and it can manipulate it if it wants to. So this allows you to build user space threading libraries, and I just think that's one of the coolest things ever. Okay, last thing to do here, there's one thing missing, which is, remember, we're going to be IREDing up the stack, so we need to make sure that we have the return address for where the signal handler returns to. Because remember, your signal handler will run, it'll access its arguments, that's these guys. And then when you reach the end of your signal handler, you have a return. So we have to know where to go back to. Where do we go back to? Well, the problem is we have to restore this machine context back to the process so that the program, where it was interrupted by the signal, can resume running. And so we have to get back into the kernel. And the way that this is done is that the address to return to that's put onto the stack is just a hook to this system call called sigreturn. And you can look this up. Now I'm curious because I have sigreturn and sysreturn here. So you'll have to Google this to see which one is right. I have to go look myself. Sometimes I find things in my slides and I don't remember why I put them there, but this may be accurate. But sigreturn is this really simple little system call, and its whole job in life is to handle the cleanup from a signal delivery. So that's what this thing does. Just restores the interrupted process's CPU context from where it is on the stack, which at that point will be just above the arguments that the signal handler looked at. So all that stuff gets cleaned up, machine context is restored. Okay, so we modified the user stack. We have to point the ESP to the new top of stack. So that's what this picture indicates here. We just need to make sure that the caller's ESP is modified so that the signal handler sees what it's supposed to see. Okay, now do signal is done, and as you can see on the right, do signal return. So now kernel stack frames, kernel thread stack frames are going away because functions are returning. Then, oops, wrong direction. The kernel IRETs, whatever handler it was in, IRETs, and so all that stuff is restored. We end up back in user mode, executing the signal handler. So we're back to the signal handler now. Okay, so the signal handler can do whatever it wants. You'll notice that the kernel thread stack is empty. Everything is fine there. All the important details are stuffed onto the user process stack. And this means that we can make system calls and do whatever we want from a signal handler. And it doesn't interfere with any of the mechanisms that are going on inside the process or inside the kernel on behalf of the process. This is pretty freaking cool, I think. Okay, Now, let's say the signal handler finishes. So remember, this is the user process stack, and our kernel thread stack is empty right now because we're not in the kernel, we're in the process. So we return at the end of our signal handler, and so the sig return address is what's invoked, and that invokes this sysreturn system call, and we end up trapping into the kernel. So all of this information gets pushed onto the kernel thread stack. Now, as I say here, this is the register state of the signal handler, okay? This is at the end of the signal handler. And so what sigreturn does is it just takes this register state of the interrupted process and plops it in where it's supposed to go. And the idea is now when we iRead out of the kernel again, we'll go back to the part of the process that was running when the signal fired off or was delivered. Okay. Oh, and there's another important detail here. Along with any changes to the CPU context made by the signal handler, if the signal handler happened to muck with these details, those details are also plopped into the kernel thread stack. Okay. Now you might say that seems like a security risk. It really isn't, because the kernel doesn't use these things except to restore when going back to the process. So if the process blows its own brains out by mangling register state or instruction pointer state or whatever, the kernel doesn't care. It's just that when the kernel irets back into the process will explode into a million bits, and the kernel will say, oh, that sucked, that didn't go well, and it'll just terminate the process. So not a big deal if the user process does something silly with those register values. Okay, then sysreturn returns back to the user process. It also, of course, gets rid of all of this stuff, so you can imagine that it also needs to update the stack pointer to make sure that when sysreturn returns, that it's pointing the stack back to where it should be, pointing the stack pointer back to where it should be. Okay, awesome. I think this is just one of the coolest things. Are there any questions about this? If you think of any, feel free to shoot them into the chat. Hopefully it makes sense generally, and hopefully you see this ability to save the machine context elsewhere and restore it is a foundational building block of operating system implementation. It's how we build multitasking, and it is so unbelievably useful. We use it in many other different contexts, and signal handling is a perfect example of that. So hopefully you will grow to appreciate this ability to save and restore machine contexts as much as I do, because it's just remarkable. Okay. So I was mentioning that you might be in a system call when a signal occurs. And so what we're saying here is that the system call is actually interrupted by the signal. The kernel tends to need to deal with this somehow, because it needs to record or know or remember that this thing was interrupted so that the kernel doesn't lose its own mind. You know, let's say that we're in a disk queue. We're blocked on a disk IO, and we're in a disk queue when a signal occurs. Do we leave it in the disk queue? We have to become ready. Do we record that we were in the disk queue, and then when the signal is delivered, we go back? That's fraught with a lot of peril for reasons that I may try to show you in the remaining slides. But the bottom line is the kernel actually doesn't leave it in the disk queue. It actually takes it out and it puts it back into the ready queue. So that means that that system call was interrupted, and we need to communicate that to the user process, that this call was interrupted. And so generally the way that this is handled is the kernel will return this special error code called EENTER for system calls that get interrupted by a signal delivery. So maybe you were using man to look at various operations in the first project, and you may have noticed EENTER as a possible error code, and that would mean that the system call can be interrupted by signal delivery. It's not fatal. All the kernel really needs to do, or I shouldn't say the kernel, the user program simply needs to retry the operation. That's all you need to do if you get back EENTER on a system call. Now, if all you need to do is just retry it if you see EEnter come back? Well, another option is that the kernel could just retry the system call for you. And there's a really clever mechanism for it to do that. And so, as I say on the slide, read and write are examples of something that may be automatically restarted if the signal is delivered within a certain window of the read or write call. Other ones need, they actually are specified to report that they were interrupted. Sleep operations are a great example. If you're passively waiting, the specification is that you must report EEnter if you were wakened early by a signal. So, as it says on the slide, nanosleep is an example of a call that must return EEnter and say how long it actually slept. Or I'm sorry, the amount of time remaining to sleep when it's interrupted. Okay, now if the process is in a system call, remember the stacks. This is always the answer, it seems. If the process was in a system call when it received a signal, then guess what? The kernel is going to be able to see the interrupt number, and it's going to know, hey, the process trapped into the kernel. It's going to be able to see the register state, so it'll know that you're performing this system call or that system call, because remember, that's indicated by a specific number. Alternately, the process may be in some block queue. So regardless of the state, the kernel is going to be able to tell that a system call had been initiated, and it will be able to take appropriate steps to report the interruption of that system call. So there's one of two things it can do. The first one is to simply go in, and remember, normally we return the result code to the system call in EAX, since we're on IA32. So we just set EAX to EEnter, and we set up the process so that when when it is resumed, it goes back into user space, and the process will see, oh, I was EEntered, and I need to try again. The second option is way more clever, and it involves actually backing up the instruction pointer, because it turns out that the trap instructions are always a specific size, at least on x86. And so, a software trap instruction is going to be 2 bytes. Sysenter is going to be 2 bytes. So all the kernel has to do to get the process to retry the operation is back up the instruction pointer 2 bytes. That'll rerun the instruction, and it'll end up back inside the kernel. So it's a really clever mechanism for making sure that the system call is retried. Okay, last thing to talk about is this beast called long jump. I don't know if you're familiar with long jump and sig long jump. Is anybody familiar with these beasts? Have you gotten to have experience with them? Long jump and sig long jump are what are called non-local go-tos. Now, you've all probably been taught that go-to is a terrible thing to use in your program, and this is true. There are very specific scenarios in which you should use go-to, particularly centering around error handling in code like C or C++. That tends to be the only circumstance in which you really want to use go-to. Now, imagine go-to, but instead of just going to another part of the same function, you can go to a completely different function. That's freaky. That's what long jump and sig long jump do. Now, the other function has to already be running. And so if you have function A calls function B, calls function C, calls function D, and D wants to go back to function A, that's okay. But D can't go off to some other function Q that's not even invoked at the time. So there's some nuances there. But anyway, long jump and sig long jump are strange beasts, and they tend to appear with signal handling, which is crazy. Okay, so let me show you basically what you're allowed to do. You're allowed to sig long jump out of your signal handler to another part of your program. And this has been used in the past for mechanisms like send a signal to reset the process, send a signal to reset the server program and cause it to reload its state. So you, sig hup is the one that's normally used. Hup stands for hang up. And so you might send a sig hup to a process and that restarts it and reloads the configuration. So you would sig long jump out of the signal handler to go do that. Not recommended, but that's how we used to roll. So as I say on the slide, does performing a sig long jump from a signal handler break the delivery mechanism? And you look at the stacks and hopefully you see that the answer is not at all. Sig long jumping out of a signal handler won't affect anything. Because the first thing is that do signal always removes the pending state for a signal about to be delivered before it's delivered. So we remember that we have this sig return thing that goes back into the kernel and then back out. And that won't run if we long jump out of the signal handler. But that's fine because as far as the kernel is concerned, the signal no longer needs to be delivered. It's already taken care of. And so the kernel doesn't require that the handler complete in any way to actually complete the delivery of the signal. Okay. Now, the other thing that I want to say here, because I want to kind of cut this short, is that the signal delivery mechanism doesn't affect the kernel stack. Remember, the kernel stack is always empty when we go back to the user process. If we're in the signal handler in the user program, the kernel stack is empty. So jumping out of the signal handler to another part of the program doesn't affect the kernel thread. So we don't mangle anything in the kernel. The kernel's safe. And we're just discarding this interrupted process register state, which is kind of the whole point of long jump and sig long jump anyway. When you do a non-local function goto, we're saying we don't want this. We don't want to use it. We're just leaving it behind. So, oops, wrong direction. How do I get confused on buttons at this point in my life? So yeah, this is what I was saying. We don't want to restore this execution state, which is why it's okay that we don't invoke sig return here. So basically everything works perfectly fine, even when we use these crazy magic functions like long jump and sig long jump to get out of a signal handler back into another part of our program. Okay, that is 99% of what I wanted to say. Give me one more minute and I'll tell you one more little thing why this is actually a really terrible idea to use long jump or sig long jump. In general, I would actually encourage you to avoid them at all costs. One of the things that can be interrupted by a signal handler is a call to the memory allocator. And all of you have had experience writing memory allocators, and you know how complex the data structures are for managing memory allocations within the user process. Some of you, probably most of you, also found ways to corrupt the heap while you were writing your memory allocator. Now, if you are in the middle of a malloc call and a signal goes off, and in your signal handler, you jump to another part of your program using long jump or sig long jump, that malloc call didn't finish, which means you now have a corrupted heap. And so almost always, you're playing with fire if you use long jump and sig long jump in your programs. So while they're really interesting functions to understand, they're also really scary to use. And it's definitely playing with fire carelessly when you do that kind of thing. So nonetheless, I love that this mechanism is robust and clean, even in these unusual usage patterns. The signal delivery mechanism, to me, is one of those highly elegant parts of how Unix operating systems are implemented. Okay, I will shut up. What we're going to do next time is start talking about memory allocation within the kernel. It's a very important and challenging problem to solve. So we actually have 2 lectures about kernel allocators, and we'll pick that up next time. So I'll see you then.